table. The periodic table was developed by a Russian chemist called Dmitry Mendeleev. Mendeleev worked in the late 1800s to develop his theories about how the periodic table of elements should be arranged. His original thoughts were how to create a nice simple worksheet or table for chemists to use in their labs and for chemistry students to use in their classrooms to help them understand the relationships between different atoms. His table is on the right-hand side. It's compared to what we use today in our classes on the left. As you can see, some of what Mendeleev used to develop his table were actually pretty good. There are gaps and questions in what he had written down, but for the most part, both are pretty close and are actually spot on in some cases. Mendeleev used atomic masses in his table. This can be seen in the numbers that he used to define what the actual elements were. He used hydrogen as 1 and lithium as 7. These are actually pretty close to what he had thought. But if you look, there are some missteps along the way, and some of his placements are not quite right. For instance, he put lithium in the same group as hydrogen, which is fine if you're looking at the group, but as far as looking at the entire period, it's not right. He placed it in the same period as sodium, where it should be in the same period as beryllium. We no longer use Mendeleev's table today. Instead, we only use the one that you see in front of you. Our periodic table does come from Mendeleev's experiments, though. Mendeleev predicted that there should be some sort of pattern that develops as you go through the periodic table. And he was correct. There are many, many trends that develop. We're only going to talk about a few of them, though. We do arrange our periodic table in numerical order just like Mendeleev did. However, we don't use the atomic masses of the elements. Instead, we use the atomic number. If you go back to the atom video, you'll understand why. Atomic number comes from the number of protons that are in the nucleus of the atom. This is much more stable to count across the periodic table instead of atomic masses. Atomic masses tend to change depending upon the isotope. So we use atomic number rather than atomic mass. As you move across a period from left to right, the trends tend to follow this pattern. Atomic radius tends to decrease, whereas the ionic radius, electronegativity, first ionization energy all tend to increase. Electronegativity is how attractive an element would be at grabbing an electron off of another element. Fluorine is the most electronegative element on the periodic table. First ionization energy is the energy that you need to put into the system in order to take off the first electron off of an atom. Now, if fluorine would be the most electronegative element, meaning it wants to get an electron very easily, then it would also make sense that it would take a lot of energy to take off that first electron. And it's true, it does. Now, except for hydrogen and helium, the rest of the table, as you move from left to right, tends to follow the pattern of metals to metalloids and then to nonmetals. There are also patterns as you move down in a group. As you go from top to bottom, the atomic radius, ionic radius, all tend to increase, whereas electronegativity and first ionization energy tend to decrease. Francesium is the least electronegative element in the table and has the lowest first ionization energy. Compared to fluorine, it is at the complete opposite end of the table and of the spectrum. Now the properties also change as you move down. As you move down the table, you go from nonmetals to metalloids to metals. This is most apparent on the right side of the table. Now, inside of a group that's one column on the table, they all tend to have the same kind of properties. Let's look at one of the groups in particular in the table. Let's look at group 14. And let's look at the first three in particular: carbon, silicon, and germanium. The reason these elements have the same properties is because they tend to have the same number of valence electrons. In this case, they have 4 valence electrons. Valence electrons are those electrons that are all the way at the end of the carbon, silicon, or germanium atoms, at the ends. This property is true for every group in groups 1, 2, and 13 through 18. Groups 3 through 12 are known as the transition metals. In some cases, if you go from top to bottom, they do have the same number of valence electrons, but it's not always true. There are some cases where you have an element that has 2 valence electrons on top of an element that has 4 valence electrons, and that one's on top of something that has 3 valence electrons. So the transition metals really don't fit into this same group. Now, if you do look at the table, you notice that the lanthanide and actinide series are pulled out and put underneath the table. This is purely because we want the table to fit on one single page. If we were to put the lanthanide and actinide series inside the table where it belongs, the table would be too big and too hard for you to read. So, what have we learned through this video? We learned how Mendeleev originally organized his table and how it compares and contrasts to today's table. We also learned how trends exist in the periodic table and how Mendeleev predicted some of them.